On November 11, 2025, something that shouldn't exist appeared in the lens of a telescope on the Canary Islands. The object that every physicist said would shatter into cosmic dust was still intact. Not damaged, not fragmenting, whole. Let me be clear about what we're dealing with here. For 2 weeks, 3i Atlas had been invisible, hidden directly behind the sun from our perspective here on Earth. 2 weeks of radio silence, 2 weeks where the most intense thermal assault a comet can face was happening without any human eyes watching. And when it finally emerged from that solar furnace on November 11th, astronomers didn't find debris. They didn't find fragments. They found a single, coherent nucleus with an ion tail streaming behind it like nothing had happened. Think about that timeline for a moment. October 29th and 30, this interstellar visitor made its closest approach to our Sun, swinging through perihelion at a distance of 1.36 astronomical units. That's somewhere between the orbits of Earth and Mars, which sounds comfortably distant until you understand what solar radiation does to ice and rock at that range. The thermal stress alone should have fractured it. The outgassing pressure from vaporizing ices should have blown it apart from the inside. This wasn't supposed to be survivable for an object with 3i Atlas's profile. But here's what makes November 11 so significant. The astronomers behind that telescope weren't amateurs with backyard equipment hoping for a lucky shot. David Jewitt and Jane Liu are names that carry weight in planetary science. These are the researchers who discovered the first Kuiper Belt objects beyond Neptune, who fundamentally changed how we understand the architecture of our solar system's outer reaches. When they point a telescope at something and tell you what they saw, you listen. And they were using the Nordic Optical Telescope, a 2.56-meter instrument perched at Roque de los Muchachos Observatory on La Palma. This isn't cutting-edge space telescope technology, but it's a serious professional instrument with the optical quality needed to resolve fine detail on distant objects. When Jewitt and Liu processed their images from that night, they saw what nobody was certain they'd see. One object. Not two. Not a debris field spreading out in a diffuse cloud. A single nucleus, still bound together, with an ion tail extending 0.7 degrees across the sky behind it. Now I want you to understand the context that makes this so shocking. Just weeks earlier, another comet, C2025 K1 Atlas, had approached the Sun along its own trajectory. Different object, different origin, but similar perihelion distance. That comet didn't make it. As it approached solar heating, the nucleus fragmented, broke apart, and dispersed into the kind of debris field that everyone expected 3i Atlas to become. That's the normal story. That's what comets do when they get too close, when the thermal gradient across their surface becomes too extreme, when the pressure from sublimating gases overwhelms whatever structural integrity holds them together. So when 3i Atlas disappeared behind the Sun on October 21st, 8 days before its closest approach, the astronomical community had every reason to expect the worst. That solar conjunction placed it directly between us and the Sun from Earth's perspective, creating a natural observational blackout. No ground-based telescope could track it. No space telescope in Earth orbit could observe it without pointing dangerously close to the solar disk. For those 2 weeks, 3i Atlas was on its own, facing the most intense radiation it would ever encounter during its passage through our solar system, and we were completely blind. Think about what that uncertainty feels like for researchers who've been tracking this object for months. You've gathered data, you've built models, you've calculated trajectories and predicted behaviors, and then your subject vanishes into the glare of the Sun right before the moment that will determine whether your models were accurate. It's like watching a tightrope walker step behind a curtain just before the hardest part of the crossing. You can calculate the physics all you want, but until they emerge on the other side, you don't actually know. The astronomy community didn't stay quiet during that blackout, of course. Social media lit up with speculation. Amateur astronomers compared notes. Professional researchers debated in conference calls and email chains, running thermal stress models and fragmentation simulations, trying to predict what the first post-perihelion images would show. Would there be anything left? Would they see a dispersing cloud of fragments, each piece following slightly different orbital paths as they separated? Or would there be nothing at all, the entire object sublimated into gas too diffuse to detect? November 8th came and went with no definitive observations. November 9th brought some preliminary attempts, but the comet was still too close to the solar glare for clear imaging. November 10th improved the viewing angle slightly, but weather and scheduling limited what could be captured. And then November 11th arrived, and Jewitt and Lou at the Nordic Optical Telescope got their window. When those images came through, showing an intact nucleus with visible structure, and that ion tail stretching across 0.7 degrees of sky, it didn't just answer the question of whether 3I Atlas survived. It posed an entirely new question, one that's actually harder to answer. How? If you want to understand how a cosmic object defies every prediction we had about its destruction, you need to see what happens next, because the survival itself is just the beginning of this mystery. But before we go deeper, hit that like button if this mystery already has you hooked, and subscribe with notifications on, because December 19th is coming fast. That's when Hubble, Webb, and ground-based telescopes will capture the data that could either solve this or make it even stranger. You'll want to be here when those results drop. Now, let me show you the physics that should have destroyed this comet. Stay with me, because what the deeper analysis reveals makes the intact survival look simple by comparison. But first, we need to understand exactly what was supposed to destroy this comet, and why every physicist who looked at the data said it wouldn't make it through perihelion in one piece. Let me walk you through the physics that should have killed 3I Atlas, because understanding why it was supposed to die makes its survival so much stranger. Comets are not solid rocks. They're mixtures of ice, dust, and rocky material, held together by gravity and the cold of deep space. When a comet approaches the Sun, solar radiation heats the surface. That heat penetrates inward, reaching layers of volatile ices that have been frozen solid for potentially billions of years. Water ice sublimates, going directly from solid to gas without passing through a liquid phase. Carbon dioxide ice does the same, but at lower temperatures, which means it starts out gassing even farther from the Sun. Carbon monoxide is even more volatile, vaporizing at distances where water ice remains solid. This outgassing creates pressure. Gas forming inside or just below the surface has to escape somewhere. If it escapes evenly, the comet might remain stable. But comets aren't uniform objects, they have cracks, voids, pockets of different composition. Gas finds the weak points and exploits them. That pressure can split a nucleus along fault lines or blow chunks of material off the surface. And if the heating is rapid enough, if the temperature gradient becomes too steep, the thermal stress alone can fracture the nucleus even before outgassing pressure becomes a factor. Now add rotation. Most comets spin, and that rotation creates asymmetric heating. One side faces the Sun longer than the other. The sunlit hemisphere heats up, outgassing increases, and that outgassing creates a reactive force, a jet of gas and dust pushing in one direction. That jet exerts a force on the nucleus, potentially spinning it faster or wobbling its rotation axis. If the structural integrity is already compromised by thermal stress and internal pressure, this rotational force can be the final factor that pulls it apart. This isn't theoretical physics. We've watched comets fragment. We have images of nuclei splitting into 2, 3, sometimes dozens of pieces, each trailing its own tail of gas and dust as they slowly drift apart. C 2025 K1 Atlas, the comet I mentioned earlier, is a perfect example. As it approached perihelion, observers started detecting changes in brightness, subtle variations that suggested structural instability. Then, closer to the Sun, the fragmentation became obvious. Multiple condensations appeared in the coma, the cloud of gas and dust surrounding the nucleus. Each condensation was a separate piece of the original nucleus, now independent, each sublimating and creating its own miniature tail. That was the expected fate for 3I Atlas. The mathematics of thermal stress, the physics of outgassing pressure, the observational history of comets at similar perihelion distances, all of it pointed toward fragmentation. Maybe not catastrophic disintegration, but at least some level of breakup, some visible evidence that the nucleus couldn't hold together under the assault of solar heating. And then there was the timing problem. October 21st, 2025. 8 days before perihelion, 3I Atlas entered solar conjunction from Earth's perspective. Imagine drawing a straight line from Earth to the Sun. Now imagine 3I Atlas positioned somewhere along that line, on the far side of the Sun. From our viewpoint, the comet is directly behind the Sun's glare. You can't point a telescope at it without pointing dangerously close to the solar disk, which would not only overwhelm your detector with light, but could potentially damage the instrument. This wasn't a brief transit. a few hours of inconvenient geometry. The conjunction lasted through the most critical period, October 21st to October 29th, the approach phase, October 29th to 30, perihelion itself, and then several more days afterward as 3. I-Atlas began receding but remained too close to the Sun's position in our sky for safe observation. We're talking about roughly 2 weeks where the comet was going through its most intense thermal environment, and we couldn't watch. Think about what that means from a scientific standpoint. You have an object of immense interest, an interstellar visitor that originated in another star system, passing through the most revealing moment of its trajectory. Every hour of those 2 weeks would have provided crucial data about how interstellar comets respond to solar heating, how their composition compares to native solar system comets, whether they show unusual fragmentation patterns or unexpected resilience. And all of that data was lost to geometry, to the simple fact that Earth and the comet and the Sun aligned in a way that made observation impossible. The astronomical community did what it could with the situation. Observations from spacecraft not positioned along the Earth-Sun line could theoretically see the comet, but those instruments are scheduled months in advance, and their viewing angles weren't optimal. Ground-based observers prepared for the earliest possible post-perihelion detection, calculating exactly when 3, I-Atlas would emerge far enough from the solar glare to be safely observed. Amateur astronomers networked, sharing information about weather conditions and telescope availability, hoping to catch the first glimpse, and everyone wondered. The speculation wasn't idle curiosity. Researchers had models running, predictions about what the comet's light curve would look like if it fragmented versus if it remained intact. They prepared observing proposals. For both scenarios, if it survived, here's what we'll look for. If it fragments, here's how we'll track the pieces. The uncertainty wasn't comfortable, but it was part of the process. November 8th brought the first marginal detections, images where 3 I-Atlas appeared as a faint smudge still too close to solar glare for detailed analysis. November 9th improved slightly. November 10th gave clearer views, and observers started seeing a single condensation, not the multiple sources that would indicate fragmentation. But you couldn't be certain from those early images. Resolution was limited. Maybe the fragments were too close together to resolve individually. Maybe the viewing angle hid the separation. Then November 11th delivered the verdict, and nothing about that verdict made sense with what was supposed to happen. David Jewitt and Jane Liu pointed the Nordic Optical Telescope at 3 I-Atlas on November 11, 2025, and the images they captured weren't just scientifically valuable, they were deeply strange. Let me describe what a fragmented comet looks like. When a nucleus breaks apart, you don't see clean separation immediately. The fragments remain relatively close together, bound loosely by their mutual gravity and all moving along nearly identical orbits. From a distance, you might see an elongated smudge instead of a point source, or multiple bright condensations embedded in a shared coma. As days pass, the fragments drift apart, each following a slightly different trajectory because each has slightly different outgassing patterns, creating slightly different non-gravitational forces. Eventually they separate enough to resolve as distinct objects, each with its own tail. That's not what Jewitt and Liu saw. Their images showed a single, point-like nucleus. Not elongated, not multiple condensations, one object, compact and coherent, and extending from that nucleus, an ion tail stretched across 0.7 degrees of angular distance, about 1.5 times the apparent width of a full moon. That ion tail was clear evidence of active outgassing. Solar wind was ionizing gases streaming off the nucleus and sweeping them into a long, narrow tail, pointing directly away from the Sun. This was a comet behaving exactly like comets behave when they're actively sublimating, except it was doing so as a single unified object after passing through conditions that should have torn it apart. Now, November 11th wasn't the first time anyone had imaged 3 I-Atlas. Back on July 23rd, 2025, when the comet was still 3.8 astronomical units from the Sun, well before perihelion, the Hubble Space Telescope captured images that revealed something unusual. Even at that distance, 3 I-Atlas showed a prominent antitail, a jet of material pointing toward the Sun instead of away from it. That antitail extended roughly 1 million kilometers in the sunward direction, a striking feature because standard cometary physics says tails should point away from the Sun. Radiation pressure from sunlight and the solar wind push gas and dust outward. Yet here was material streaming in the opposite direction. Those July images were taken when 3I Atlas was relatively far from the Sun, when outgassing was still modest, when the comet was in what should have been a stable, predictable phase of its approach. The anti-tail suggested a symmetric outgassing, jets firing preferentially from one hemisphere, likely the sunlit side. Large dust particles, less affected by radiation pressure than smaller grains or ionized gas, could follow ballistic trajectories that appeared to move sunward from certain viewing angles. It was unusual, but not unprecedented. Other comets have shown similar features under specific geometric conditions. But comparing the July 21st Hubble images to the November 11th Nordic Optical Telescope images revealed evolution. In July, the comet had a diffuse coma with that prominent anti-tail. By November, post-perihelion, the structure had grown more complex. The ion tail was now clearly visible, something that hadn't been prominent in the earlier images. That makes sense. Closer to the Sun, higher outgassing rates, more gas being ionized by solar radiation, more material for the solar wind to sweep into a visible tail. But the complexity went beyond a simple ion tail. When observers processed the November images, applying contrast enhancement to bring out faint details, they counted at least 7 distinct jets emanating from the nucleus. Not a uniform coma expanding equally in all directions. Discrete jets, each one a concentrated stream of gas and dust being expelled from a specific active area on the nucleus surface. 7 separate source regions, all outgassing simultaneously, all contributing to the overall activity level. And the sunward jets, they were still there. Even post-perihelion, even after the most intense heating, 3I Atlas continued showing material being ejected toward the Sun. The anti-tail had evolved, changed its structure as viewing geometry shifted and as the comet's orientation changed, but it persisted. That meant the asymmetric outgassing that created it in July was still active in November. Whatever regions on the nucleus were producing those sunward jets, they'd survived perihelion intact and functioning. Jewitt and Liu weren't the only ones observing. The International Comet Quarterly's network of observers, including experienced amateurs like Michael Buchner and Frank Niebling, independently confirmed the intact survival. Their images, taken with smaller telescopes and different processing techniques, corroborated what the Nordic Optical Telescope showed. One nucleus, prominent tail, no fragmentation. Gianluca Massi at the Virtual Telescope Project in Italy, operating a robotic telescope system designed for real-time astronomical observation, captured images on November 11th and 12th that told the same story. Single condensation in the center of the coma, ion tail extending antisolar. No evidence of fragmentation or debris. Massi's images, processed and published online within hours of capture, gave the wider astronomical community confirmation. This wasn't a processing artifact in one telescope's data. Multiple independent observers, using different instruments, were all seeing the same thing, so let's establish what we know with high confidence as of mid-November 2025. 3I Atlas passed through perihelion intact. It remained a single, coherent nucleus without detectable fragmentation. It continued showing active outgassing with multiple distinct jets, including persistent sunward jets that defied standard tail geometry. Its ion tail indicated high levels of gas production, consistent with a nucleus experiencing strong solar heating. All of that would be fascinating for an ordinary comet. For an interstellar visitor, an object that formed in another star system under different conditions and has now made its first and only close pass by our Sun, it's unprecedented data. This is information about how material from another stellar environment responds to our Sun's radiation. Every detail matters. Every measurement contributes to models of interstellar object composition and behavior. But here's where the story shifts from fascinating survival to something doesn't add up. Because when scientists started calculating the energy budget required to produce what they were observing, the numbers revealed a problem. Not a small uncertainty. Not a modest discrepancy that could be explained by measurement error. A fundamental contradiction between the size of the nucleus and the amount of energy it was releasing. And that contradiction demands an explanation that nobody has yet provided. Drop a comment right now. What's your explanation for this energy paradox? Internal fragmentation, exotic ice composition, measurement error, or something we haven't thought of yet? The scientific community is genuinely divided on this, and I'm curious what you think. And if this energy budget problem just changed how you see this entire story, smash that like button. because we're about to examine the most persistent anomaly of all, those sunward jets that have been defying physics since July. Let me show you the problem, and I want you to follow the logic carefully, because this is where 3i Atlas stops being merely unusual and starts being genuinely confounding. Cometary jets aren't magic, they're physics. When ice on or just below a comet's surface absorbs solar radiation, it sublimates, turning from solid directly into gas. That gas expands rapidly, carrying dust particles with it, and streams away from the nucleus at velocities that can reach hundreds of meters per second. The gas and dust form the visible jet, a collimated stream that can extend for hundreds of thousands or even millions of kilometers before dispersing. Creating those jets requires energy. Specifically, it requires the energy to break the molecular bonds holding water ice, or carbon dioxide ice, or carbon monoxide ice together in solid form, and then to accelerate the resulting gas molecules to escape velocity. That energy comes from solar radiation. Sunlight hits the nucleus surface, heats it, and that heat is transferred to the subsurface ices. The more ice you sublimate, the more gas you produce. The more gas you produce, the larger and longer your jets become. So if you observe jets of a certain size and brightness, you can work backward to estimate how much gas must be flowing to create them. And from the gas flow rate, you can estimate how much energy is required. And from the energy requirement, you can calculate how much surface area needs to be actively sublimating to absorb enough sunlight to provide that energy. Let's look at the observations. In November, after perihelion, 3i Atlas displayed jets extending to remarkable distances. The sunward jets, those anti-tail structures visible since July, measured approximately 950,000 kilometers at their maximum observed extent. Let's call that about 1 million kilometers for easier math. On the anti-solar side, the ion tail and dust jets extended even farther, reaching roughly 2.85 million kilometers. Now those jets aren't static, they're constantly being produced and constantly dispersing. Material ejected today will be millions of kilometers away next week, and fresh material will take its place near the nucleus. To maintain jets of that size and brightness, the nucleus has to continuously produce gas and dust at rates high enough to replace what disperses. Observational data from the jet brightness and structure, combined with models of gas expansion and dust dynamics, allowed researchers to estimate the mass loss rate. Near perihelion, when solar heating was at its peak, 3i Atlas was estimated to be ejecting approximately 5 billion tons of material per month. That's about 167 million tons per day, or roughly 2 million tons per hour. For context, that's like launching the mass of a large cruise ship off the nucleus every single hour, continuously for weeks. Producing that level of mass loss requires enormous energy input. The energy needed to sublimate water ice is about 2.8 million joules per kilogram. If we assume a significant portion of the ejected material is water ice or comparable volatiles, 5 billion tons per month translates to an energy requirement of roughly 3 times 10 to the 18th joules over that period. That's 3 million trillion joules, an almost incomprehensible amount of energy, but it's coming from sunlight, and the sun produces vast amounts of energy, so there's no shortage of available power. The question is whether 3i Atlas can intercept enough of that solar energy to drive the observed activity, and that depends on surface area. The more surface area you have exposed to sunlight, the more energy you can absorb. Solar flux at 1.36 AU, 3i Atlas's perihelion distance is about 1,000 watts per square meter. Not all of that energy goes into sublimation. Much of it is reflected or radiated back as infrared heat. But if we assume reasonably efficient energy conversion, we can calculate how much surface area is needed to absorb the 3 times 10 to the 18th joules required. The calculation gives you an answer that's straightforward to state but deeply problematic. You'd need a surface area equivalent to a sphere roughly 23 kilometers in diameter. If the entire surface of a 23-kilometer sphere were actively sublimating at maximum efficiency, it could produce the energy output observed in 3i Atlas's jets. Here's the problem. On July 21, 2025, when Hubble imaged 3i Atlas at 3.8 AU, astronomers measured the nucleus. Hubble's resolution allowed them to determine that the nucleus was compact, with a maximum diameter of approximately 5.6 kilometers. Not 23 kilometers, not even close. The observed nucleus is about 4 times too small in diameter, which translates to about 16 times too small in surface area, to produce the energy output needed for the jets we're seeing. Think about what that means. Imagine you measure a car's fuel tank and find it holds 10 gallons. Then you observe that car driving 1,000 miles without refueling. The math doesn't work. Either your measurement of the fuel tank was wrong, or the car is somehow getting energy from somewhere other than its tank, or there's a fundamental misunderstanding of how the car operates. That's the situation with 3I Atlas. The nucleus is too small to produce the observed jets using the standard physics of cometary outgassing. It's like watching a golf ball produce the exhaust plume of a semi-truck. The size of the source doesn't match the size of the output. Let me be clear about the uncertainties here. Measuring a comet nucleus from Earth, even with Hubble, involves assumptions. The nucleus is embedded in a bright coma, so you're trying to isolate a faint point source within a cloud of light. You model the light contribution from the coma and subtract it, leaving what you hope is the nucleus signal. If your coma model is wrong, your nucleus size estimate is wrong. So there's measurement uncertainty. Maybe the nucleus is bigger than 5.6 kilometers, but even doubling the size estimate doesn't solve the problem. A nucleus twice the diameter still has only 1/4 the required surface area. You'd need to argue that the Hubble measurement was off by a factor of 4 in diameter, which would require errors large enough to be immediately obvious to the researchers who made the measurement. And those researchers, Jewitt and Liu among them, are not inexperienced observers making rookie mistakes. They know how to measure comet nuclei. They've done it for dozens of objects. If the measurement was that far off, they'd know. So if the measurement isn't wildly wrong, what explains the discrepancy? One possibility is internal fragmentation. Maybe the nucleus isn't a single solid object but a loose collection of fragments held together by weak gravity, like a rubble pile. When it approaches the sun, those fragments don't separate cleanly, but gaps open up between them, exposing internal surfaces to sunlight. Suddenly you have not just the outer surface sublimating, but internal surfaces as well, multiplying your active area without changing the outer dimensions. From a distance, it still looks like one object because the fragments haven't drifted apart, but internally it's a complex fractured structure with far more active area than its external diameter suggests. That's plausible. We've seen comets that are structurally weak, held together by gravity barely strong enough to resist the outgassing forces trying to blow them apart. If 3I Atlas is in that category, internal fragmentation could expose enough surface area to explain the energy budget. Except, we have no direct evidence of internal fragmentation. The images show a compact nucleus, not an elongated or irregular shape that would suggest separated fragments. Maybe the resolution isn't sufficient to see the separation. Maybe the fragments are close enough together that they blend into a single bright source. But that's speculation, not observation. Another possibility involves the composition. If 3I Atlas has unusually high concentrations of supervolatile ices, carbon dioxide or carbon monoxide, those substances sublimate at lower temperatures and require less energy per kilogram than water ice. Maybe the jets aren't primarily water vapor. Maybe they're dominated by these more volatile species, which would reduce the total energy requirement and ease the surface area problem. But spectroscopic observations haven't shown unusual composition so far. The visible gases are consistent with typical cometary ice ratios. There's no strong evidence that 3I Atlas is compositionally exotic enough to solve the energy budget problem through supervolatiles alone. A third explanation is hidden reservoirs. Perhaps there are subsurface pockets of highly volatile material that are being released through cracks or vents, concentrating outgassing in a way that creates large jets from small active areas. Instead of sublimation happening evenly across the surface, it's focused through specific openings, amplifying the apparent activity level. Again, possible, but difficult to verify without higher resolution imaging or close-up observations that can resolve the nuclear structure in detail. We're left inferring processes we can't directly observe. And then there's the explanation that nobody in the mainstream scientific community wants to lead with, but that sits in the background of every discussion about this object. Maybe our assumptions about what 3I Atlas is are incomplete. Maybe there's something about this interstellar visitor that doesn't fit the standard cometary model. Which brings us directly to the scientific debate that's been playing out in journals, conferences, and very publicly on social media. Let's focus on one specific feature that's been visible since July and that continues to defy easy explanation: the sunward jets. In standard cometary physics, tails point away from the sun. This isn't a subtle tendency. It's a direct consequence of fundamental forces. Solar radiation exerts pressure on small particles, physically pushing them outward. The solar wind, a stream of charged particles flowing constantly from the Sun, sweeps ionized gas away from the comet at high speed. Both forces act in the anti-solar direction. That's why comet tails always point away from the Sun, regardless of the comet's direction of motion. You could have a comet moving toward the Sun, and its tail would still stream behind it in the anti-solar direction. So when you see jets pointing toward the Sun, you need an explanation for why material is moving in a direction opposite to the forces that should be pushing it away. And 3i Atlas has shown prominent sunward jets since July, through perihelion and into November. This isn't a brief anomaly, it's a persistent structural feature. The angular length of these sunward jets has been measured at various times. In July, at 3.8 AU from the Sun, the antitail extended roughly 1 million kilometers in the sunward direction. By November, post-perihelion, the structure had evolved, but sunward jets remained clearly visible. The angular extent in November images was somewhat less prominent than in July, but that could be a viewing geometry effect. As 3i Atlas moved along its orbit and Earth moved along ours, the angle from which we viewed the comet changed, altering the apparent size and shape of features that are actually three-dimensional structures extending into space. But the persistence of sunward material is undeniable. 7 months of observations, from pre-perihelion through perihelion and into post-perihelion phases, all show jets that defy the standard anti-solar tail geometry. That demands an explanation. The most straightforward natural explanation involves particle size and ballistics. When a comet nucleus ejects material, not all of that material is the same size. You have molecules of gas, water vapor, and carbon dioxide and carbon monoxide, each individual molecule tiny and easily pushed by radiation pressure. You have small dust grains, micrometers or tens of micrometers in diameter, also strongly affected by radiation pressure. And you have larger particles, millimeters, or even centimeters across, with enough mass that radiation pressure has a much weaker effect. Those large particles follow ballistic trajectories. They're ejected from the nucleus at some initial velocity, determined by the speed of the gas flow carrying them. Once they leave the immediate vicinity of the nucleus, they're in free flight, governed primarily by gravity and their initial momentum. Radiation pressure still acts on them, but for particles large enough, that pressure is negligible compared to gravitational and inertial forces. If the nucleus is rotating, and if the active regions producing jets are on the sunlit hemisphere, those regions are facing the Sun. Material ejected from a sunlit, sun-facing region leaves the surface moving at least partially in the sunward direction. Large, massive particles in that ejector follow their ballistic paths. From certain viewing angles, especially if Earth happens to be positioned such that we're looking at the comet from a direction roughly perpendicular to the Sun-Comet line, those sunward moving particles can appear to form a tail pointing toward the Sun. It's a geometric effect combined with particle physics. The particles aren't actually defying radiation pressure. They're just massive enough that radiation pressure doesn't dominate their motion, and they're being observed from an angle that makes their ballistic trajectory look like a sunward tail. This explanation has been published in scientific literature. Researchers have modelled the dynamics of large dust particles in cometary Comet, showing that under specific conditions of viewing geometry and outgassing patterns, antitails can appear purely through natural processes. There's even an arXiv preprint, authored by a team analysing 3i Atlas observations, titled something along the lines of The Physics of Cometary Antitails as Observed in 3i Atlas, which lays out the mathematical framework for how large dust grains can create the observed sunward structures. And there's precedent. Comet C 2014 UN271, also known as Bernardinelli-Bernson, showed similar sunward enhancements in images captured as it approached perihelion. That comet, notable for having an exceptionally large nucleus, displayed a coma that wasn't symmetric. One side appeared brighter, enhanced, extending farther than the opposite side. Analysis showed that this enhancement was directed generally sunward, a consequence of asymmetric outgassing from the sunlit hemisphere, combined with large dust particles following ballistic paths. So sunward jets aren't unique to 3i Atlas. They've been seen before. They have natural explanations that don't require exotic physics or unknown forces. The fact that 3i Atlas shows this feature prominently and persistently is unusual in degree, perhaps, but not in kind. But let me point out a subtlety here. Natural explanations exist and are well-founded in physics. That doesn't mean they fully account for everything we're observing. The antitail in 3I Atlas is particularly prominent, persisting over a long period and showing complex structure. The number of distinct jets, at least 7 visible in processed images, suggests multiple active regions, each producing its own outgassing pattern. The evolution of the antitail from July to November indicates that whatever processes are driving it, they remained active and strong through perihelion. And there's a question of degree. If the sunward jets are produced by large dust particles following ballistic trajectories, where is all that dust coming from? Large particles require more energy to lift off the surface than small particles. You need strong gas flow to entrain and accelerate them. That brings us back to the energy budget problem. Producing enough gas flow to carry large dust particles into sunward trajectories, creating jets that remain visible over millions of kilometers, requires significant energy. And we've already established that 3I Atlas's observed size doesn't easily account for its energy output. So the antitail has natural explanations, but those explanations don't eliminate the underlying mysteries. They shift the question from why are there sunward jets to how is the nucleus producing enough activity to create such prominent sunward jets? And that's a question that leads directly into the scientific debate that's been intensifying as more data comes in. Because not everyone in the scientific community is comfortable with the standard explanations. Some researchers look at the accumulated observations, the energy budget discrepancy, the persistent sunward jets, the intact survival through perihelion, and they see a pattern that doesn't quite fit, and when patterns don't fit, that's when scientific debates get interesting. If you've followed astronomical news over the past few years, you've probably heard of Avi Loeb. He's a professor of astrophysics at Harvard, former chair of the astronomy department, prolific researcher with hundreds of papers to his name. He's also become a polarizing figure in the scientific community because of his willingness to publicly speculate about possibilities that most researchers prefer to avoid. Loeb was the scientist who, back in 2017, suggested that Oumuamua, the first confirmed interstellar object detected passing through our solar system, might not be a natural comet or asteroid. He pointed to its unusual acceleration, its elongated shape inferred from light curves, its lack of visible cometary activity, and argued that these characteristics were consistent with what you'd expect from an artificial object, perhaps a light sail propelled by radiation pressure. Most of the astronomical community disagreed, providing natural explanations for each of Oumuamua's oddities, but Loeb didn't back down. He published papers, he wrote a book, he founded a research project specifically to search for potential evidence of extraterrestrial technology. So when Loeb turned his attention to 3I Atlas and publicly called its behaviour profoundly surprising, people listened, though not always sympathetically. Because Loeb brings credibility and controversy in equal measure, he's a serious scientist with genuine expertise. He's also the scientist who's willing to say things that make his colleagues uncomfortable. In late 2025, after the November observations confirmed 3I Atlas's intact survival, and as more data about its jets and activity levels became available, Loeb published commentary analysing the object. He noted the non-gravitational acceleration, the fact that 3I Atlas's trajectory showed deviations from a purely gravitational orbit. Non-gravitational acceleration isn't unusual in comets. Outgassing creates thrust, like a very weak rocket engine, and that thrust alters the orbit slightly. The effect is measurable and expected, but Loeb calculated the magnitude of the thrust required to produce the observed orbital changes and compared it to the estimated mass of the nucleus. His conclusion: to generate the observed acceleration, 3I Atlas would need to be ejecting between 10 and 20% of its total mass, not 10 to 20% of its mass over its entire lifetime, 10 to 20% during the period of close solar approach, over a few months. Think about that. If a comet ejects 20% of its mass, it's undergoing catastrophic disintegration. You don't lose that much of your structure and remain a coherent object. Yet 3I Atlas showed no signs of fragmentation. It remained intact, coherent, displaying organized jet structures. Loeb's point was that the numbers didn't reconcile. Either the mass estimate was far too low, or the acceleration measurements were wrong, or something about the object's behavior didn't fit standard cometary physics. Let's be absolutely clear about the scientific consensus here. The overwhelming majority of astronomers studying 3I Atlas consider it a natural comet, not an artificial object. While Loeb's speculation generates headlines and public interest, it remains a minority viewpoint that is not supported by mainstream planetary science. The artificial origin hypothesis faces a fundamental scientific problem. It makes no testable predictions. What specific observation would distinguish an artificial object from a highly active natural comet? Without defined criteria, the hypothesis doesn't advance understanding. It simply labels mysteries as potentially artificial, without providing a framework to investigate further. Most researchers analysing 3I Atlas are pursuing entirely natural explanations: internal fragmentation exposing hidden surface area without visible separation, supervolatile ice composition, carbon monoxide dominated rather than water dominated, asymmetric internal structure focusing outgassing through specific vents, or measurement uncertainties in the nucleus size due to the bright surrounding coma. All of these explanations fit within established physics and make predictions that December observations contest. The burden of proof for extraordinary claims remains high in science, and we don't fully understand it yet. Is not evidence for artificial origin, it's evidence that we need better data, which is exactly what December 19th will provide. The mainstream scientific community responded with a mix of measured critique and outright dismissal. Many researchers reiterated the natural explanations we've already discussed. Internal fragmentation could expose more surface area without visible breakup. Supervolatile ices could increase activity levels without requiring massive mass loss. Measurement uncertainties in the nucleus size could account for the energy budget discrepancy. The antitail has precedent and doesn't require exotic physics. Other scientists pointed out that invoking artificial origins is scientifically unproductive, without specific testable predictions. What would an artificial object do differently from a natural comet? If you can't define observational criteria that would distinguish between the two hypotheses, then the artificial hypothesis isn't adding scientific value. It's just speculation that happens to grab headlines, and some researchers were more blunt. Loeb's history with Oumuamua, his tendency to publicly speculate before definitive data is available, his willingness to court controversy, all of that has made parts of the astronomical community wary. There's a concern that premature speculation undermines public understanding of science, that it feeds into conspiratorial thinking, that it distracts from the legitimate scientific work being done to understand these objects through rigorous analysis. But here's the complexity. Loeb isn't wrong that 3I Atlas is displaying unusual behaviour. The energy budget discrepancy is real. The persistent sunward jets are real. The intact survival through perihelion, while not impossible, was unexpected. Multiple independent observations confirm these features. So the question isn't whether 3I Atlas is unusual. It clearly is. The question is whether that unusualness demands explanations outside the current framework of cometary physics, or whether the framework just needs refinement and better data. Legitimate scientific debate exists. Papers are being written. Observations are being analysed. Some researchers are focusing on compositional models, trying to determine if specific ice mixtures could explain the high activity levels. Others are working on structural models simulating how fractures and internal voids might expose hidden surface area. Still others are refining the orbital analysis, checking whether the non-gravitational acceleration is as large as initially calculated, or whether there are subtleties in the trajectory fitting that could reduce the discrepancy. This is how science progresses. Anomalies appear. Researchers propose explanations. Data is gathered to test those explanations. The model that best fits the data becomes the accepted understanding until new anomalies appear and the cycle repeats. Right now, 3I Atlas is in the anomaly phase. We have observations that challenge simple interpretations. We have competing explanations. We don't yet have enough data to definitively rule in or out the various hypotheses. And then there are the rumours, the claims, circulating on social media and fringe websites that have latched onto 3I Atlas as potential evidence for something beyond natural astronomical phenomena. One claim that gained traction in late October was that a radio signal had been detected coming from 3I Atlas on October 24th, just days before perihelion. The claim was specific enough to sound credible, a narrow-band signal implying artificial origin detected by amateur radio astronomers. Let me be clear, there is no verified, peer-reviewed evidence of any radio signal from 3I Atlas. Radio telescopes routinely monitor comets, detecting natural emissions from ionized gases in the coma and tail. Comets produce radio noise. That's normal physics. If someone detected a radio signal on October 24th, it was almost certainly natural cometary emission, possibly amplified by increased outgassing as the comet approached perihelion and misinterpreted as something unusual. The problem with these rumours is that they muddy the scientific conversation. Researchers trying to understand 3I Atlas through careful observation and analysis have to contend with public perception shaped by unverified claims and sensationalised speculation. That doesn't help anyone. It doesn't help the scientists doing the work, and it doesn't help the public trying to understand what's actually happening. What does help is waiting for the next round of observations, the data that will either resolve the current mysteries or deepen them further, and that data is coming very soon. Mark your calendar for December 19th, 2025. That's the date when 3I Atlas makes its closest approach to Earth, swinging through space at a distance of 0.65 astronomical units, roughly 97 million kilometers, or about 60 million miles from our planet. That might sound distant, but in astronomical terms, it's remarkably close. For comparison, at perihelion in late October, 3I Atlas was 1.36 AU from the Sun, but much farther from Earth because of orbital geometry. On December 19th, the comet will be closer to us than it's been at any point during its passage through the inner solar system. That proximity matters, because proximity equals data. The closer an object is, the more light we receive from it. More light means better signal-to-noise ratios. Better signal means higher resolution images, more detailed spectra, more precise measurements. Everything we want to know about 3I Atlas becomes easier to determine when it's at closest approach. And the astronomical community knows this. Observation time has been scheduled on multiple premier instruments. The Hubble Space Telescope, the same instrument that captured the July 21st images showing the 5.6-kilometre nucleus, has scheduled observation windows in mid-December. Hubble's ultraviolet spectrograph will be pointed at the comet, analysing the light emitted by gases in the coma. Different gases emit ultraviolet light at different wavelengths. By measuring which wavelengths are present and at what intensities, you can determine the chemical composition of the material outgassing from the nucleus. 1. Key measurement Hubble will attempt is the sulfur-to-oxygen ratio. In cometary science, this ratio is a fingerprint of formation conditions. Different regions of a protoplanetary disk, depending on their temperature and chemistry, produce ices with different sulfur and oxygen abundances. By measuring the ratio in 3I Atlas's coma, astronomers can infer something about the environment in which this comet formed, billions of years ago, in a star system potentially many light-years away. The James Webb Space Telescope, humanity's most powerful infrared observatory, has also scheduled observations in December. Webb's near-infrared instruments can detect thermal emission from the nucleus itself, not just the reflected sunlight. That thermal signature provides data on the nucleus temperature, which in turn constrains models of how heat is distributed across the surface and how efficiently the nucleus absorbs and radiates solar energy. Webb can also detect specific molecular signatures in the infrared, looking for carbon dioxide ice, carbon monoxide, organic molecules, all of which emit characteristic infrared light as they sublimate and interact with sunlight. Ground-based telescopes worldwide are preparing as well. Professional observatories with large apertures and advanced spectrographs will track 3I Atlas throughout December, capturing high-resolution images and spectra. Amateur astronomers, equipped with increasingly sophisticated equipment and processing software, will contribute observations that, when combined, provide near-continuous monitoring. This distributed network of observers ensures that even if weather or technical issues affect one site, others will capture the data. What will these observations reveal? Several critical questions could be answered. First, the jet velocity measurements. By using spectroscopy to analyse the Doppler shift of light emitted by gas in the jets, astronomers can determine how fast that gas is moving. Faster jets require more energy, which feeds back into the energy budget calculation. If the jets are moving slower than expected, that eases the energy requirements. If they're moving faster, the discrepancy worsens. Second, the chemical composition. Confirming the relative abundances of water, carbon dioxide, carbon monoxide, and other volatiles will tell us whether 3I Atlas has an unusual composition that could explain its high activity levels. If it's rich in supervolatiles, that supports the compositional explanation for the energy budget problem. If it has typical cometary ice ratios, that explanation becomes less viable. Third, structural integrity. High-resolution imaging might reveal whether the nucleus is truly a single object or whether there are signs of fragmentation too subtle to detect in earlier observations. If the nucleus appears elongated or shows multiple bright condensations, that would suggest internal fragmentation, supporting the hidden surface area explanation. Fourth, non-gravitational forces. By precisely measuring the comet's position over multiple nights and comparing those positions to predictions based on gravitational dynamics alone, astronomers can refine the estimate of the thrust produced by outgassing. Better measurements of the non-gravitational acceleration will either confirm or revise Loeb's calculations about mass loss rates, and there's a deadline pressure here that's important to understand. After December 19th, 3I Atlas will begin receding from both the Sun and Earth. As it moves farther away, it receives less solar heating, so outgassing decreases. Jets become fainter, harder to observe. The coma dims, and most critically, the comet becomes a more difficult target for telescopes, requiring longer exposure times and larger apertures to gather sufficient light. By early 2026, 3I Atlas will be too faint for detailed spectroscopy. By mid-2026, even large professional telescopes will struggle to track it. Hubble and Webb will move on to other targets. Ground-based observers will lose the comet in the glare of the Milky Way, or find it positioned inconveniently low in the sky from their locations. The window for gathering high-quality data is measured in weeks, not months. This is our best chance. December is when the scientific community will gather the observations needed to resolve, or at least constrain, the mysteries that 3I Atlas has presented. The energy budget discrepancy, the sunward jets, the chemical composition, the structural integrity, all of these questions have the best chance of being answered during this close approach window. In roughly 35 days from mid-November, we'll have data that could fundamentally change our understanding of this object. We'll know whether the natural explanations hold, or whether the anomalies persist and deepen. We'll have measurements precise enough to rule out some hypotheses and support others, and the scientific community will begin the process of synthesizing that data into a coherent picture of what 3I Atlas is and how it works. But regardless of what December reveals, the story of this interstellar visitor has already changed how we think about comets, about interstellar objects, about what can survive the intense environment near the Sun, and that broader significance is worth understanding. Step back from the specific measurements and orbital mechanics for a moment, and consider what 3I Atlas represents. This is an object that didn't form in our solar system. It coalesced from the protoplanetary disk surrounding another star, somewhere in the Milky Way galaxy, billions of years ago. It orbited that star, or perhaps was ejected from its birth system early in its history and has been travelling through interstellar space ever since. Cold, isolated, untouched by any star's warmth for eons, until it encountered our Sun, until it fell inward along a hyperbolic trajectory, accelerating as gravity pulled it closer, experiencing increasing solar radiation, heat, light, charged particles, all of it building to a crescendo at perihelion on October 29th and 30th, 2025. For this object, that was a unique event. It will never return. Its trajectory will carry it back out of the solar system into the vast emptiness between stars, and unless it encounters another star, which is statistically unlikely over timescales shorter than millions of years, it will never again experience what it experienced in late October. We happen to be watching. Humanity, in this brief moment of our technological development, has telescopes capable of detecting and tracking interstellar visitors. We have spectroscopy to analyze their composition. We have orbital dynamics to calculate their trajectories. We have models to interpret their behavior. And because we were watching, we captured data about an object from beyond our solar system, undergoing an event it will never repeat. That data has scientific value, regardless of whether 3I Atlas is behaving unusually. Even if it were a perfectly typical comet, its interstellar origin would make it valuable. Comets in our solar system formed from the same protoplanetary disk that formed the Sun and planets. Their composition reflects the chemistry of that specific disk at the specific location and time they formed. But 3I Atlas formed elsewhere, from different material under different conditions. Comparing its composition to native solar system comets tells us whether cometary ices are universal, whether the chemistry that produces water-rich, volatilaric objects is the same around different stars, or whether there's diversity that reflects different stellar environments. And if 3i Atlas is unusual, if it's displaying behaviours that challenge our current models, then its scientific value multiplies, because unusual objects are how science progresses. When observations don't fit existing models, that's when you learn something new. You either refine the models to accommodate the new data, or you develop new models that explain both the old data and the new anomalies. Either way, your understanding deepens. So what have we learned so far? We've learned that interstellar comets can be structurally resilient. 3i Atlas survived conditions that fragment many native comets. That tells us something about how interstellar objects are built, perhaps about the thermal or radiation history they experienced in their birth environment, or during their journey through space. Maybe they're more cohesive, more compacted by the cold of interstellar space. Maybe the lack of thermal cycling, the absence of repeated heating and cooling as they would experience orbiting a star, allows them to maintain structural integrity better. We've learned that interstellar comets can be highly active. The jets and mass loss rates observed in 3i Atlas are comparable to or exceed those of similarly sized native comets. That suggests abundant volatiles, ices that readily sublimate, which implies formation in a cold, volatileric region of another star's protoplanetary disk. That's consistent with theories of planet formation, where volatile ices are more abundant in the outer regions of disks, beyond the frost line where water ice can condense. And we've learned that observing interstellar objects is hard. They arrive with little warning. Their trajectories give us limited windows for observation. They're often faint, distant, moving quickly across the sky. 3i Atlas is one of only a handful of confirmed interstellar objects ever detected. We've had Oumuamua in 2017, we've had 2i Borisov in 2019, and now 3i Atlas in 2025. That's 3 objects in 8 years, from which we're trying to build a general understanding of interstellar populations. It's statistically absurd trying to characterize a population from 3 examples, but it's the data we have, which makes every detail about 3i Atlas important. Every measurement, every spectrum, every image contributes to that sparse data set. When the next interstellar visitor arrives, perhaps in 2027, perhaps not until 2032, we'll compare it to the 3 we've already observed. Similarities will suggest common properties. Differences will define the range of diversity. Slowly, over decades, we'll accumulate enough data to say meaningful things about interstellar objects as a class. But there's also the immediate question of the Mars Reconnaissance Orbiter images. On October 3, 2025, as 3i Atlas was still approaching perihelion, MRO, NASA's spacecraft orbiting Mars, captured images of the comet from a unique vantage point. MRO was positioned such that it could image 3i Atlas from a perspective unavailable to Earth-based telescopes. The resolution wasn't extraordinary, approximately 30 kilometers per pixel, but it was an independent dataset, a different viewing angle, potentially revealing details not visible from Earth. Those images have not been publicly released as of mid-November 2025. There are understandable reasons. NASA's data processing pipeline has standard procedures. Images from spacecraft go through calibration, validation, archiving, all of which takes time. Researchers who propose the observations typically get a proprietary period to analyze the data before public release. That's normal scientific practice, designed to ensure that the people who invested time and effort into planning observations get to publish their results before the data becomes freely available to everyone. But the delay has fueled frustration in the broader community. Observers who've been tracking 3i Atlas eagerly want any additional data, especially from unique perspectives like MRO's Mars-based viewpoint. Social media discussions speculate about what those images might show and why they haven't been released. Some of that speculation veers into conspiracy, suggesting that the images reveal something unusual and are being withheld, intentionally. That's almost certainly not the case. Bureaucratic delays, processing schedules, and proprietary data periods adequately explain the timeline, but the frustration is real and understandable. When an object is generating this much scientific and public interest, delays in data release feel obstructive, even when they're procedurally justified. Regardless of when or whether those MRO images become public, the broader picture remains. 3i Atlas has presented more questions than answers. We're learning, but each answer seems to reveal deeper layers of complexity. Here's where we stand in mid-November 2025. An interstellar visitor passed through the most intense environment it will encounter in our solar system and emerged intact when many expected it wouldn't. The images showing that survival also revealed activity levels that seem inconsistent with the object's measured size. Jets that defy standard geometry have persisted for months. The physics doesn't quite add up, at least not with the data and models we currently have. And in 35 days, we'll have the best opportunity we're ever going to get to gather the data needed to make sense of it. December 19th is approaching, Hubble and Webb are scheduled, ground-based observatories are preparing. The astronomical community is coordinating efforts to maximize the scientific return from this close approach window. Spectra will be captured, images will be processed, measurements will be refined. What will those observations show? Maybe they'll resolve everything neatly. Maybe the spectroscopy will reveal an unusual ice composition that explains the high activity. Maybe higher resolution imaging will detect subtle signs of fragmentation that account for the energy budget discrepancy. Maybe the refined orbital measurements will show that the non-gravitational acceleration isn't as extreme as initially calculated, easing the mass loss problem. If that happens, the scientific papers will be written, the models will be updated, and 3i Atlas will become a well-understood, if unusually active, interstellar comet. Or maybe the observations will deepen the mystery. Maybe the composition will be unremarkable, the nucleus will appear intact and coherent, and the energy budget discrepancy will persist. Maybe new anomalies will appear, features that weren't visible in earlier observations but that become apparent with better data. If that happens, the scientific debate intensifies. More exotic explanations get serious consideration. Researchers start designing follow-up observations trying to catch 3i Atlas before it recedes beyond reach. Either outcome is scientifically valuable. Resolution is satisfying, but it's the mysteries that push understanding forward. If 3i Atlas turns out to be explainable within current frameworks, we've confirmed that those frameworks are robust. If it remains anomalous, we've identified a gap in our understanding that needs filling. Both results advance knowledge. But here's what makes this moment special. You're witnessing this unfold in real time. Most of science happens slowly, data accumulating over years, papers published in journals that take months to review, discoveries announced long after the observations were made. But with 3i Atlas, the timeline is compressed. The observations are happening now, the discussions are happening now, the uncertainties are unresolved now, and you're part of the community watching as they either get resolved or deepen. That's rare. That's the privilege of living in an era where telescopes can detect objects like this, where communication networks can disseminate data almost instantly, where you can follow along as scientists grapple with observations that don't fit neatly into existing models. You're not reading about this in a history book, looking back at discoveries made generations ago. You're here, now, as it happens, and your attention matters. When public interest focuses on an object like 3i Atlas, it increases the visibility of the research. More telescope time gets allocated, more resources go toward analysis. Scientists know that their work is reaching beyond academic journals, that there's a community eager to understand what they're discovering. That feedback loop between researchers and the public strengthens the entire endeavour, so stay informed. When December 19th passes and the first results from those observations start appearing, whether in press releases in preprint archives or in social media posts from the researchers involved, pay attention, follow the updates, read the analyses, ask questions, engage with the process of discovery. This is your opportunity to be part of something larger than yourself, part of humanity's effort to understand the universe we inhabit. Because whatever 3i Atlas turns out to be, whether it's a natural comet behaving strangely, or something that forces us to expand our models in unexpected ways, it's a visitor from beyond our solar system. It's a messenger from another star carrying information about environments we can't directly access. And for a brief moment, a few months in late 2025, it passed close enough for us to study it in detail. In 35 days, we'll have data that could answer the questions we've been asking since July. The energy budget discrepancy, the sunward jets, the structural resilience, the chemical composition. All of it will become clearer, or at least better constrained, when the December observations are complete. What will we discover? That's the question I want you to answer in the comments. Drop your location. Where in the world are you following this story? What's your prediction for December 19th? Will the observation solve the energy paradox or reveal something even stranger? And subscribe now if you want to be here when those results come in, because I'm covering this the moment data is released. In 35 days, we're going to find out whether 3I, Atlas, is an unusually active natural comet or something that forces us to rewrite cometary physics. The answer is coming, and you're going to witness it unfold. I'll see you in the next one.